Alrighty, Math Project 4, Linear Model Review with Laplace, the perfect cup of coffee. Alrighty, so the scenario is you're at a cafe, and you know what? The coffee's too hot to drink. Classic, you burn your tongue. Well, okay, what's the fastest way to get the cup of coffee to the right temperature and also get the longest enjoyment time? By enjoyment time, I mean the time that time interval where the coffee is cool enough to drink but also warm enough to enjoy. So it's that period before it gets too cold to not be enjoyable anymore. So there's a couple different scenarios. First scenario, just waiting for the coffee to cool. Yeah, that's what a lot of people do. It's fine. B, taking the coffee outside to cool faster, assuming it's in the wintertime. We're going to look at that. And then C, pouring in some creamer to cool the coffee instantly. And we're going to look at all of these three scenarios. First, case A, just waiting it out. And in all these cases, the coffee is going to start at 200 degrees at 0 time. And then at 2 minutes, the coffee is going to have dropped to 190 degrees. That's the same for all three cases. The drinking temperature that we're going to try to target, the range, the zone, is going to be 140 to 120 degrees. That's the optimal drinking temperature. So we're going to start with a basic Newton's law of cooling equation right here, where we have big T is big T is temperature, small t is time, TR is the temperature of the room, which changes in case B because you're going outside. K is a constant rate of heat exchange, which we'll solve for, and which is also a constant throughout the project. We're trying to figure out what the temperature, or what the time will be when the temperature is 140 degrees. Because that is when the optimal range starts as the coffee is cooling down. So we're trying to figure out how long you have to wait for this specific cup of coffee, given the initial values and the secondary measurements. There's several ways to do this. We're going to start with a Laplace transformation, and then we're going to go and verify it using just separation, because it is a separable linear differential equation. So we're going to convert to Laplace using the forms on the table. And we're going to then rearrange everything to solve for big T of S, which we do here. And then we're going to convert back. Okay, I did write the generic forms right here. I thought I wrote them on the previous slide, but I guess not. Must have missed that. After we solved it algebraically for T of S, then we're going to convert back the Laplace back to calculus using partial fractions. And this is something super nice. So what we get here when we do all that math, we can actually use this throughout the rest of the project, because in case B and C, the core right here is still the same. You just add more stuff onto the side. So that's really nice. You don't actually ever have to do this step again. You can just reuse this information. Now that we have a solution, we can use separation to verify it, because separation is a simpler process. There's not as much converting. What we're going to do is we're going to put all the big T's on one side, all the temperatures, and we're going to put all the small t's on the other side. We're going to use a little substitution, integrate it, and then you have to solve for plus C, of course, which we do here. Take the exponent of it to get rid of the natural log. This side simplifies, it's just a constant, and then you get this. Oh, look at that. That versus that. It's the same. That's good. That's what we're hoping for. And then we're going to solve for K using our secondary measurements. So our initial conditions we used to solve for the plus C. That was at time equals 0, the temperature is 200 degrees. Our secondary measurements is at time equals 2 minutes, the temperature is 190 degrees. So it's obviously decreased some. You can use that information to solve for the rate of change, which is K. So yeah, I mean, it's just algebra. You plug in your initial conditions, you solve for K, do some natural log stuff, you get k right here. And this threw me off a little bit because I was expecting to get a negative k, but then I put it into the equation and realized that, oh, it's actually just negative here, because the negative k shows that the temperature is decreasing over time. Okay, now that we have all that, now that we have an actual equation with only two variables, time and temperature, we can plug in temperature and solve for time. So what time will it be when the cup of coffee reaches a certain temperature? Well, if it's 100, we're trying to find the range of 140 and 120. So we're going to start with 140 to get our lower time bounds. Plug it in, rearrange everything, right? And what I do typically is I'll write it out like this, and then I'll plug it into my calculator, because I think that gets more of an exact result instead of rounding it several times throughout the equation, from my experience anyway. So here we get time is 15.5 minutes. That's the wait time until you can start drinking the cup of coffee, in case A, if you were just going to sit there and wait. And then 120 degrees is when it gets just when it gets too cold to actually enjoy. So that's 23.5 or 23.9 minutes. 23.9 minus 15.5 to get our range of enjoyment time between 140 and 120 degrees. It's 8.4 minutes. That's really important to remember. 8.4 minutes. We'll see that come up again later. Hint, hint. Something I noticed here, the wait time is double. I was like, that's insane. I didn't realize, like, you're waiting 15.5 minutes and you can only enjoy it for 8.4 minutes. Like, the wait time, it's not double, but it's almost double, and it probably feels like it too, because it usually takes a while to wait for something. Okay, case B. We're going to change it up a little bit. We're going to actually take the coffee outside, and that way it can cool down faster for a period of time. So we're going to, oh no, there we go. After waiting for 2 minutes with our secondary measurement at temperature equals 190 degrees, I was done waiting, so I went outside. It was 40 degrees outside, and I got cold, so I came back in after 8 minutes for being outside, so with a total of 10 minutes, right? We can model this equation, we can model this situation with a unit step equation. Basically, it turns certain functions on and other functions off at specific times. So at time equals 2, I'm going to turn on the function for room temperature to be 40 degrees, and I'm turning off the function of room temperature to be 70 degrees. Then when time equals 10 minutes, so I spent 8 minutes outside plus the 2 minutes inside, I'm going to turn off the function for 40 degrees outside, and I'm going to turn on the function for 70 degrees inside. It's a little bit confusing. What I realized actually is that you only need to do this for the room temperature function. You don't need to do this for the whole equation. So that really simplifies it. And it ends up looking like this. I wrote it out in a piecewise function first, kind of shorthand. This isn't an exact piecewise function, but I just wrote this out for my own notes. And then to apply it, the u is, it's not an index variable. It's kind of a weird, it's a weird concept to get, because this entire part is only ever going to be 0 or 1 in all these cases, right? So that's a little bit confusing, just because u doesn't come up like this ever before. I've never used a unit step function before. But essentially, a time equals, when time is when time is after 2 minutes, this will equal 0, so it'll all go away. And then when time equals any time after 2 minutes, right, this will be 1, so that'll kick in essentially. They're either on or off, the functions themselves. So this will turn on. So they'll all affect the equation differently depending on what time range it's in. Yeah, okay, so this is the room temperature, right? And you can actually simplify this because some of these are the same. So, come on. So u of t minus, or u times t minus 2, all right, I added those all together, plugged it into the original equation here for t of r, and I expanded it. I expanded my k, so I get 4 different terms here. And then we're going to do the same thing we already did with Laplace transformation. It's just a little bit more complicated because we have these two variables which are a little bit harder to solve for. So these are, right, I already said they're exactly the same as case A. So they actually invert back to those. This is a little bit difficult because there's a formula you have to use right here. You have to use this formula to invert the two terms in the equation that shift the temperature based on the time. So I did that. It took me excuse me, it took me a while to figure that out. But once I did one of them, I was able to do the second one pretty easily because they're basically the same, except there's a negative sign that's different and there's a 2 instead of a 10, right? So 10 and 2, they're different because one turns off at 2 seconds and the other one turns on at 10 seconds, right? So yeah. And then once you invert those back to calculus from Laplace transformation, you get this, and you plug them back in. Okay, so I rewrote it again here with all of our k's. I just used k for all the math because I didn't want to write negative 0.04002 every single time when I could just write k. So I did that, and then I wrote it all out here. Now we're going to figure out how to use the time shift. So after being outside for 8 minutes at room temperature 40 degrees, at time equals 10 minutes, I go back inside where room temperature equals 70 degrees. Let's see where the time is when the temperature of the coffee is 140 degrees. We are going to assume, for starters, that it reaches 140 degrees while I'm outside. So we're going to turn off the function for when I go back inside because I haven't gone back inside yet, so it's not being applied. I did all this math. I got 12.13 minutes, which means that, oh, actually, I did go back inside before the temperature reached 140 degrees of the coffee. So I need to resolve this and just turn both my functions on. So let's do that. And I just used a computer because I did not want to write the whole thing out again. And I was, yeah, I didn't want to do that. That took way too long. So with both u functions equal to 1, so both of them are turned on, right? Both functions are switched on. So I went outside and then I came back in. I get, it's like 12.93 or something, but it essentially rounds to 13 minutes for case B when the temperature is 140 degrees of the coffee. When the temperature is 120 degrees, I get a time of 21.4 minutes. It's super interesting here. This is what's interesting. The enjoyment time is the same for case A and B. That's really interesting. The wait time is different, but the enjoyment time, is ultimately the same. And I was kind of surprised because I was expecting it to be different, I guess, because the wait time was different. But no, this here zone, you can see in the graph, is the same. But so green is 120, blue is 100, or hold up. Green is 140, blue is 120. So you can see it's too hot, it's just right, and then it's too cold. Okay, case C. This time I'm staying in the cafe, but I'm pouring creamer into my coffee. It instantaneously reduces the temperature by 20 degrees, but also decays with time. So you can't just subtract 20 degrees from the temperature in part A, since that would only work for the instant after 2 minutes, 170 degrees, where previously it was 190 degrees. We need to use a delta function with a coefficient of 20 to decrease the differential equation by a decaying 20 degrees, starting at a C value of time equals 2 minutes. Alrighty, so That's pretty simple. A delta equation is literally just delta times t minus 2. Similar idea where it's going to turn on at a certain time, 2 minutes, but it's going to remain on, and it's going to decay with the equation instead of just always be 20. So converting it to Laplace transformation, I have a generic formula here. It's actually super, super easy. Negative 20. Yeah, anyway, that was one of the easiest things the whole time. I was like, wow, that's nice when I got to it. That's a nice break from case B, which is overly complex. I threw it into a computer along with case A and B to see the comparison on the graph. And wouldn't you know it, 8.4 minutes for enjoyment time. It's the same. I was like, how is the enjoyment time the same for all three cases? But the wait time is a lot less for case C, understandably so, because you poured creamer in it. You get 10.9 minutes to cool down to 140 degrees and 19.3 minutes to cool down to 120 degrees. And this here is just this, it's all the Laplace stuff. We've already kind of been over this whole idea. But yeah, again, these two terms are exactly the same as they were on both case A and B. The only thing that's changing here is the delta, this delta part, which is always going to be on after time equals 2 minutes. And we're always evaluating after time equals 2 minutes. So you could just say, well, that's on. That's not too bad. Same property as case B, by the way, in case you're curious. Yeah, I think that's pretty much it. I tried to get through it as quick as I could. That way I don't have a 30-minute long video. You could easily pause it at any point in time to look at the equations if you're curious. All the math does work. I double-checked everything. So hopefully this project makes more sense than my last project. My main takeaways, I was extremely surprised that the enjoyment time was all the same in all three cases. It was 8.4 minutes in all three cases. I was very surprised. I almost had thought I had done something wrong, but I guess that's just how it works. So that's really cool, actually. I was thinking for sure in case C, when you pour the creamer in, the enjoyment time is going to decrease, but it didn't. I was like, okay, well that's weird. Oh, I thought it was a much better project than other projects because this is something I could actually do and apply like almost daily. I mean, whenever I drink coffee or warm liquid, I'm trying to cool down, right? Pouring creamer in it is the best option, so that's good to know. I do that sometimes because I just like the cream, but also cools it down really good. So yeah, good to know, and thanks for watching.